Ever wondered how to get the best Wi-Fi reception in your house, given all those floors and walls which can interrupt the signal? Where to position the router and signal boosters, then where people should use their devices to get the best reception? There are so many combinations. It would make it very labour intensive to move things around and try all the different positions. But complex scenarios like this can be modelled by mathematical equations. Not the 6 minus what equals 4 type equation, really complex ones. Additionally, metamaterials are materials that have a structure that take their properties beyond what is possible from the material alone, often meaning they behave in unexpected ways. I'm Jack Taverner, and I spoke to Nader and Getter from the University of Pennsylvania about how his metamaterials can be used to find fast solutions to many tricky maths problems.
Computers, of course, can solve this type of equation, but usually the way they do it is that they do it by simulation, and that usually takes time. So our goal was to see whether we can do it in different way, hopefully much faster, in order to achieve solution of this type of problems. We wanted to see whether we can design materials that when we send waves into the materials can actually give us the solution to these types of equations.
When Nader says waves, he's not talking about the actual sea, but electromagnetic waves. They form a spectrum that includes the radio waves used to broadcast music to your car, microwaves like you'd use to heat up food, the visible light we see all around us, and even X-rays and gamma radiation. Those last two you really want to limit your exposure to, though. If you do visualise these waves like the sea, the size of the gaps between the waves decreases for each part of the spectrum, from radio to microwave to light and beyond. That means their wavelength is getting smaller. But waves can also vary in intensity, how high their peaks are, and their phase, what point in the wave you're at, top, bottom, or anywhere in between. Changing these intensity and phase properties is a way of storing information within the wave itself.
One of the interesting characteristics of waves, like microwave, is that the waves can go through each other and can interact with materials. So that would give rise to faster solution because waves propagate with the velocity of light.
It sounds like a cunning plan, but how do you create something to have these interactions? Nader explained.
We have designed a material structure you can visualize is just like a piece of plastic, and then you create air holes into this plastic. We like to call it like a Swiss cheese. And the location, the size, and the shape of these air holes in this piece of plastic Swiss cheese is the one that actually relates directly to the equation we would like to solve. The plastic itself is not something special. These materials that we have is a form of, very low-loss polystyrene plastic, which does not absorb the microwave.
So this means that microwaves can propagate or move through the material.
Now, these waves go through this structure, and strength and the phase of the wave that you send relates to the input for your equation. And then when the microwave propagates through this material and then hits some of those air holes that I mentioned, that's what actually does the magic in order to solve that equation. The waves interact with the plastic and with the holes, and when the wave is coming out, the shape and the intensity and the phase of the wave that's coming out will be proportional to the solution to that equation. So essentially, waves interacting with this specially designed material solves our equations.
The point then is by using this single, super-fast material system, you can try all the possible inputs and quickly get all the outputs to find the best solution. But how fast is this whole process happening?
Because waves propagate with the speed of light, when you put an input into the system, it takes very small amount of time for the output to come out. For the microwave, that would take us a millionth of a second. We would like to do in the future to take this concept into the shorter wavelength, like into the optics or infrared, in which case the system becomes even faster.
However, changing what type of wave is used changes the system, but excitingly, in an even more beneficial way.
The one that we actually built and tested, of course, this was just a proof of concept, that's 30 centimeters by 60 centimeters, roughly. But more important than that is what is the size with respect to the wavelength. So just to give you an idea, it's about 4 wavelengths by 8 wavelengths. The reason I emphasize that is because when we want to take this into the IR or visible light, then there also we have 4 wavelengths by 8 wavelengths. But the wavelengths in the visible and infrared is much shorter than the wavelengths in microwave. So as a result, the system can scale down to a very small. It will become in the order of few microns by few microns, kind of like a fraction of the thickness of your hair. Then you can imagine many of these plastic Swiss cheeses next to each other in a very, very small area. Each one of them can solve different equations, and these can be coupled together.
This is where things get really cool. We already have computer chips with lots of transistors packed into a small space to do calculations. But a grid of these small plastic Swiss cheese systems would have many advantages over the computers we have now.
We believe that this would be much faster because you're dealing with the waves in a much smaller volume. Another advantage that we are thinking about for the future is also low power. This may require much less energy. And one of the interesting aspects of the wave, like microwave and optical wave, can go through each other. So the massively parallel system that this can actually provide could be quite fascinating. One more thing interesting to consider for the future, to actually have this thing reconfigurable. For example, using technologies like rewritable CD that we used to have. That technology can be used for making this type of plastic Swiss cheeses in the future in the micron scale. In this case, you would think about in future, you can actually print or write your own analog computer.
That was Nader Ingeta discussing his paper in the journal Science.